Okay, it has been a couple days since I made a video, so it's about time. This is going to be a pretty lengthy video, and it's going to be one of two parts. This video is going to be, as you see, on the different types of transformations of functions. Now, transformations of functions, these are the same transformations that are used for all functions. Now, the examples I'm going to go over are specifically for linear functions. I feel like it's easier for students to start from one of the concepts that they've already mastered and then work into new functions like quadratics, absolute values, cubics, so on. These are, though, the transformations that you would use for all functions. So we have, if you add a value to the outside of the function, or if you're adding it on to the entirety of the function, then if that value we add is greater than 0, then we're going to shift the whole thing up. If the value we add on to the entire function is less than 0, so negative, then it shifts down. Now, if we take away a value, so really important here, something that students get confused on is they think this is a negative x or a negative h. This is not a negative h. This is x minus positive h. So this is taking away a value on to the input. So this is directly affecting the input, and that'll make more sense as I go through the examples, but this is directly affecting the input. Here, we directly affected the entire function. Here, this is directly affecting just the input. And if that's greater than 0, so if h is greater than 0, so if this was like x minus positive 2, which means h is greater than 0 because 2 is greater than 0, then that'd be shift to the right. So x minus 2 would be shift to the right too. If it is less than 0, and what happens there if it's less than 0? X minus a negative number, so like x minus negative 2, well, a double negative makes it positive, so it'd actually be x plus 2, and that would be shifting to the left. Now, if we change the symbol, multiply the entire function by a negative, if we multiply the entire function by a negative, that's a reflection of the x-axis. If we multiply only the input by a negative, that is a y-axis reflection over the y-axis. If we multiply the entire function by a value and that value is greater than 1, then it'll be a vertical stretch. If we multiply the entire function by a value that is between 0 and 1, so like 1/2, 3/4, 0.235, anything between 0 and 1, positive number between 0 and 1, then that would be a vertical shrink or a compression. It's going to get flattened vertically. All right. Now, if we multiply the input directly, not the whole function, but just the inputs directly, and by a value that's greater than 1, then it's going to be a horizontal shrink. So that would be a compression this way. So we're going to horizontally smash it in. So that's compression. Now, if we multiply the variables directly by a value that's between 0 and 1, so like 1/2 or 0.573 or 0.9999, then that is a horizontal stretch. Okay? Now, there are some examples on this. My students will see this. Really important, and this will come up in the examples. So actually, let me just move on from that. This will come up in part 2. So part 1, we are going to be transforming the parent function. So these are specifically all the parent functions. So remember, y equals x, that's the most basic function of a linear function. That's the parent function. That's a general linear function is y equals x, or the equation. And as a function, it's f of x equals x. Now, we are going to vertically shift this up too. Now, what that means is if we go back to here, and I want to do a vertical shift, I need to add 2 to the outside. All right, so what that means is if I add 2 to the outside, so off to the left over here, if I have f of x, and then I add 2 to it, equals, oh, I'm gonna run out of room, x. Now what's really important here is whenever you add something to the outside, whenever you add something to the entire function or you multiply the entire function by anything, you need to put parentheses around the entire function. Now, it's kind of silly because the entire function in this case is just x, but it really matters later on. So if I'm going to add to the entire function and the entire function is x, put parentheses around the entire function. All right. Or if you can think about it this way, put parentheses around everything that is on the right side of the equal sign. And then I add 2 to it. Well, I now end up with g of x because I've transformed the function. It's kind of like in geometry where you had your original point P and then you transformed it and you got P prime, right? We went from f of x and changed it to g of x with a vertical shift up 2. Let me keep this as red. So going back to the parentheses around the x, like I said, it's important for some of them, but is it important for this one? Is there any point to keep the parentheses around the x? No, there's nothing inside happening. It's just an x. So I can just drop the parentheses and I get x plus 2. And that's how I get g of x here. Now this is a table. These are the x values I plug in. And these are 2 separate functions, right? When you plug in -2 into this function, well, if I plug in -2 for x, if I substitute -2 in for x, I just get -2. If I substitute -1 in for x, I just get -1. 0, 0, 1, 1, 2, 2, right? That's the most basic linear function. And you see it here, right? When I plug in -2, I get -2. When I plug in -1, I get -1. When I plug in 0, I get 0. When I plug in 1, I get 1. When I plug in 2, I get 2. That's the parent function of a linear function. So this is f of x. Now what I want to do is I want to find out what is x plus 2. So if I plug in -2, if I substitute -2 in for x, what is -2 plus 2? 0. What is -1 plus 2? -1 plus 2 is 1. What is 0 plus 2? 2. 1 plus 2, 3. 2 plus 2, 4. So I go through and I plot these points now. So I got a -2, 0, -2, 0. I have -1, 1. I have 0, 2, 1, 3, and 2, 4. So if I grab my handy ruler, or I should say protractor in this case, I guess. I just graphed g of x. And if you look, everything was shifted up 2 units, right? And that's what I want to do. I wanted to shift everything up 2 units. And to do that, I added 2 to the entire function. So everything got shifted up 2. So when you add to an entire function, you vertically shift it up. All right, so let's move on to vertical shift down. So vertical shift down is again the same thing. You're going to add to the entire function, except you're going to add a negative number, which is the same thing as subtraction. So we're just going to subtract 2. So vertical shift down 2 means we're going to subtract 2 to the entire function. So we get f of x minus 2 equals parentheses around the entire function, which is x. And all these are going to be the parent function. All of them, we're doing the parent function for this entire video, and then minus 2 to it. Right? So I'm subtracting 2 to the entire function. And again, that will make a whole lot more sense when you watch part 2, why those parentheses are necessary, but you need to get in the habit of it. That when we do something And what I like to say is when we do something to the outside, put parentheses around the entire thing. When we do something to the inside, which you'll see in the next example, put parentheses around just the x, which we will see. So this changes the g of x because we've transformed f of x to be g of x, and that equals, well, again, are the parentheses really necessary in this? No, they are not. So we get x minus 2. Okay, so let's plug them in. Substitute negative 2 in for x. Negative 2 minus 2 is negative 4. Negative 1 minus 2 is negative 3. 0 minus 2 is negative 2. 1 minus 2 is negative 1. And 2 minus 2 is 0. So we're going to plot these points. We got negative 2, negative 4, negative 1, negative 3, 0, negative 2, and so on and so on. All right, so then we draw our line. Or I should say draw our function, and that is g of x. And again, you notice, right, we wanted to shift it down 2 units, and what do you know? Every point got shifted down 2 units. All of them got shifted down 2 units, right? Okay, got lots of these. We're doing one for every single one. Now we are going to do horizontal shift. So horizontal shift to the right. The other one we did up and down. Now we're going to do left and right. So right is on the inside. So we're going to subtract a value directly to the input. So directly to the variable. Now when we do that, that means that we want to put parentheses when we are moving to the right or to the left. We want to put parentheses around just the variable, right? We want to put parentheses around just the variable, okay? So let's go here and do this. So we have f of x, but in this case to the right, and it's always minus, always minus. See how I did not highlight the minus red? X minus is always minus when you're shifting left or right. And in this case, we are going to subtract a positive 2 because we want to go to the right 2. And this over here is a positive number. So, positive 2. So we are subtracting a positive 2, which means we are going to want to put parentheses around the x. Oof, wrong color. Around the x minus 2. Now I want to show you, let me go back to the other one. What is the difference that I did? When I was doing a vertical shift up to, I was adding to the outside and I was subtracting to the outside. You see how I made parentheses around the x? And then I did it to the outside? Because this is to the outside. However, when we're doing horizontal, that's happening to the inside. That's happening directly to the variable. So when I made the parentheses around the variable, I put the subtract 2 inside with it. Now what you're going to find out here is it really does not, in this is a special case for linear functions, is a special case that it really doesn't change anything for this special case. It will for everything else, but for this special case, it does not change anything when we're doing the parent, transforming the parent function. So this equals, well, are the parentheses necessary? Are there anything on the outside of the parentheses over here? No, so I can just get rid of them. So it's just x minus 2. Well, that's kind of silly. Didn't we just graph x minus 2? We did. Like I said, this is a special case where a horizontal shift to the right 2 is actually the same as a vertical shift down 2. And you'll see that when we graph this. The difference is the concept of it, and this is a special case. So make sure to watch part 2. Make sure to watch part 2. So let's plug them in again. -2 minus 2 is -4. -1 minus 2 is -3. 0 minus 2 is -2. 1 minus 2 is -1. And then 2 minus 2 is 0. So we plot all these points. -2, -4, -2, -4, -1, -3, so on, so on, so on. The difference is, okay, let me draw my line first. Let's draw this function. Try to be a little more accurate this time. The big difference here is when I was doing a vertical shift down 2 units, this is to the right 2. So what I'm actually looking at is I've shifted it 2 units to the right every point. Now, this is a special case where they're literally the same graph, right? This is 2 units down. This is also, oh, what do you know? This is also 2 units down. But that does not always happen. Again, please watch part 2. If you are watching this video, please watch part 2. All right? Really important. This only happens when we are doing the parent function. Only happens when we're doing the parent function of a linear function. Happens, something different happens every other time. Okay? So watch part 2. Moving on. So we're going to do our math again over here. Horizontal shift left 2 is going to mean left 2. When we go left, that means that h is less than 0. So if we're going left 2, that actually means that this is going to be a -2. Because left means less than 0. If h is less than 0, then it is a horizontal shift left. So left means negative. That means we're going to subtract a negative. So when we come over here, we're going to get f of x minus -2 equals parentheses x minus -2. Well, can't I just rewrite this? I mean, I don't like double negatives. I'm not a fan of double negatives. A double negative makes a positive. A negative times a negative is a positive. So I would just rewrite this as f of x plus 2 equals this. Okay, so let's change this to g of x now. So we're going to shift it left 2 units, right? We're subtracting a -2, just so happens to be plus. Are the parentheses necessary? Are there anything, do I need to simplify this? Do I need the parentheses? No, I do not. So I'm just left with x plus 2, right? Left with x plus 2. So -2 plus 2 is going to be 0. -1 plus 2 is going to be 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. All right, so -2, -2, 0. And then so on, so on, so on, so on. Right, and then we get g of x. Awesome. All right, now we have g of x. And again, this is to the left 2, to the left 2, to the left 2. And you guys can see, oh, x plus 2 is actually, even though it looks like it's adding, it is moving in the negative direction. We moved 2 to the left. All right. Now, it is the same. Again, this is a special case. It's the exact same as a vertical shift up 2 in this special case. I'm telling you, gotta watch part 2. I'm telling you. Okay. Move on. This is going to be another special case, but they're back-to-back special cases. Again, only for when we're transforming the parent function of a linear function. Okay, so x-axis reflection. I'm going to pull out my guide, my notes. A reflection over the x-axis is multiplying the whole function by a negative. We're going to multiply everything by a negative, right? So if I am going to multiply everything by a negative, so I got my f of x equals, and I'm going to multiply this whole thing by a negative. Then I need to put parentheses around my whole function, which is this x. I know it's silly. For this case, it's just x, but I need to multiply everything by a negative. All right. So this changes because we've transformed it. We've done a reflection. So g of x equals, okay, well, what's negative times x? Negative x, right? So you just multiply through the parentheses, you get negative x. All right, so what is negative 2? If I substitute a negative 2 in, what's negative 2? What's a negative times a negative 2? Positive 2. What is a negative times negative 1? Positive 1. What's anything times 0 is 0. What is negative times a positive 1? So what is negative times positive 1? Negative 1. And then negative 2. So we flipped it, right? We reflected it. That was the whole point. It was negative 2, negative 1, 0, 1, 2. Now it is 2, 1, 0, negative 1, negative 2. We have flipped it, reflected it. Okay, so let's plot these points. We got negative 2, 2, negative 1, 1, 0, 0, and then so on and so on. If I can get this lined up right. I told you guys it's going to be a long video. We're getting there. We are getting there. So that's g of x. And an x-axis reflection, what we've done is we've taken all of these points and reflected it over the x-axis. So 2 units, 2 units. Same thing here, taking this point. I don't know, sound effects make it better, but it's been reflected, right? 1 unit, 1 unit, 1 unit, 1 unit, 2, 2, taking every point and reflected it over the x-axis. Okay, let's do the y-axis. And if you notice, you already have written down, they're the same, and we're going to find out why they're the same for this special case. So y-axis, if you come over here, that's happening on the inside, specifically to the variable, to the input. So when I make my parentheses like I did last time, the difference here is the negative is being multiplied on the inside to the variable. So when I do my parentheses here and I put parentheses around the input, the variable, which is x, then I get it there. So last time it was on the outside, now it's on the inside. Right? Last time it was on the outside, now it's on the inside. Okay, well, I've just transformed f of x, so now it's g of x. Do the parentheses matter here? No, they don't. So you just get negative x. And you'll see that. So got the same points. They're literally the same graph. So 2, 1, 0, negative 1, negative 2. So if I plot these, right, get this point, this point, this point. Same as the last graph. They're literally identical. Same function, just found in 2 different ways. And maybe in geometry you guys did some of that, where some transformations lead to the same goal. Like if you a 90-degree or no 180-degree transformation can sometimes be the same as a y equals x transformation or reflection. I don't know if that's accurate or not, but the idea is the same because here we reflect it across the x-axis. This time we're going to reflect across the y-axis. So if I take this point and hop across, I get there. If I take this point and go across the y-axis, I get there. So this only happens, they're only identical because we're doing the parent, we're transforming the parent function. That's the only reason why they're identical. Again, watch part 2. All right. Oh my gosh, so many transformations. This is every student's favorite chapter where you go over all the transformations. Okay, vertical stretch by 2. Vertical stretch by 2. So vertical stretch by 2 means that we are going to multiply the entire function by 2. So that means we're going to put parentheses around the entire function and then multiply it by 2. So we get, actually we're going to get 2 f of x equals 2, and then times the entire function, which is in this case is just x. This case is just x, okay? So we've transformed f of x, so now we have g of x, we got a whole new function, and then 2 times x is just 2x. All right? So -2, when I substitute it in, plug in -2, what's 2 times -2? 2 times -2 is -4. -1 times 2 is -2. 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. Okay, so we have -2, -4, -1, -2, 0, 0, 1, 2, and 2, 4. So this is g of x. So how is this a vertical stretch? Well, if I think about it, if I pick this point, it has been stretched, it has been pulled up just the same as this point has been pulled down. They've been pulled apart. So it's been vertically stretched. I like to think of it as like, I don't know, as a child, if you ever played with your gum and you stretch it out, it gets a little thinner and skinnier. And that's what happens here, is it keeps, as the more you pull it, the more skinnier it gets and the more, okay? So vertical stretch by 2. Let's move on to a vertical shrink by 1/2. So instead of pulling it out, we are going to pull it in towards the x-axis. So pulling it out means pulling away from the x-axis. Pulling it or shrinking vertically means smashing it into or compressing it. Compression, vertical shrink, compression, compressing it into the x-axis. Okay? So let's go here. Again, it's vertical, so it's happening to the entire function. So we're going to get 1/2 times f of x equals 1/2 times the whole function of f of x, which is just x. Nothing fancy, it's just x, right? So we've transformed f of x to be g of x, and 1/2 times x is, what do you know, it's 1/2 x, all right? So we're going to substitute and multiply. So what is 1/2 times -2? 1/2 times -2 is -1. -1, or 1/2 times -1 is -1/2. 0 times anything is 0. 1 times 1/2 is positive 1/2. 2 times 1/2 is 1. So if I plot these, I got -2, -1, -1, -1/2, 0, 0, 1, 1/2, and then 2, 1. Okay, that's there, that's there. Okay, that looks pretty straight. That's g of x. So if you noticed, we've taken this point and pulled it in, and this point and pulled it in, compressed it, flattened it vertically, compressed it vertically, all right? And we've done so by half, right? Because this is half the distance, and this little piece is half the distance, and this, what's another good one? This is half the distance. So you've compressed it in half of how far away it was before. Okay? Fun stuff. Fun stuff. Last one for this video. I shouldn't say last one, last two. Last type of transformation for this video. So now we're on horizontal. All right, we're down to the last one, horizontal. Horizontal's happening to the inside, specifically to the variable itself, the input itself. So we're gonna stretch by 1/2. So again, really important that when it's between 0 and 1, it's a stretch. So up here, vertical stretch is when it's greater than 1. Here, it's a stretch when it's between 0 and 1. So it switches it up. Keep in mind, I would suggest that you pause maybe if you're watching this video and write these notes down. If you were one of my students, then you've already got this. Okay, so we're gonna get f of x, or not f of x actually, we're gonna get f of 1/2 times x equals, put parentheses around, 1/2 times x. Now again, this is gonna make a lot more sense when you guys watch part 2. Part 2 I think is really gonna send it home. I know this is a long video and part 2 is gonna be even longer. Okay, so this has changed. We now got g of x equals 1/2 x, because there's no point in having those parentheses up there. So we get 1/2 x. So what is -2 times 1/2? -2 times 1/2 is -1. -1 times 1/2 is -1/2. 0, 1 times 1/2 is 1/2. 2 times 1/2 is 1. Plot all these points, -2, 1, -1, 1/2, 0, right there, right there. You should, if you're paying attention to this video and not spacing off, noticed that we just did the same exact function. We just graphed the same exact g of x. It's another special case. Another special case where, look, same thing. Difference is this is a horizontal stretch, so what we're looking at is we've horizontally stretched it half the distance than it was before. It was this far away, and we're thinking about horizontally, so we want to pull, when we're thinking about stretching horizontally, we want to pull away from the y-axis because that's horizontally. We want to pull in this direction and this direction. So we were 1 away, now we're 2 away. Pulled it apart. Okay? Special case, linear function, only happens for linear function and for the parent function. Moving on. Let's go to the next one. Last one. Last one. Okay, horizontal shrink by 2. That is happening on the inside still. So it's still happening on the inside. So what do we got here? We are going to have f of, we're going to multiply by 2 x equals, and then multiplying the variable, just the variable. Again, there's only a variable in this, so it doesn't might not be clicking. This is now going to change to g of x equals, why am I switching? 2x. Okay, so we got g of x equals 2x. So let's plug in some numbers. -2 times 2 is -4. -1 times 2 is -2. 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. Okay, so -2, -4. -1, -2. 0, 0. So on, so on. Line these up pretty accurately. So this one is a horizontal shrink, so we are compressing it towards the y-axis. So we have taken the original function f of x and horizontally compressed it in. And if you kept compressing it, eventually it would just become the y-axis. All right? Fun stuff. I am going to end this video. I actually need to take a drink of water. That was a lot of talking. So, thank you for watching this video. I do hope this was helpful. However, you really need to watch part 2. Part 2 will make a whole lot more sense for this information. I know it was long, but please, please go watch part 2. Thank you for watching.